Now that we know a bit about the physical processes behind the photovoltaic energy conversion, let's take a look at the device that does this, a solar cell. In the upcoming videos, we will discuss the semiconductor physics and optics that govern solar cell behavior in more detail. You will then really get a sense of how solar cells work. In this video, we will start by trying to understand an important aspect for any electrical component, the current voltage or IV characteristic of the solar cell. Additionally, in this video, you will learn about the equivalent circuit of a solar cell, and we will discuss the influence of series and shunt resistance on the IV characteristics of a solar cell. Here we see a basic solar cell schematic. There are many different components and layers, and you will become familiar with the properties and purposes of all these layers throughout the course. In this video, we will discuss some basic parameters of a solar cell. Here we can see a typical current versus voltage characteristic of a solar cell under illumination. First off, we can see that the curve passes through the x-axis, the horizontal axis. Since current is 0 at this point essentially represents the voltage a solar cell would exhibit when disconnected from any external circuit. As such, we call this point the open circuit voltage, or VOC. Similarly, we can see the crossing of the curves along the y-axis, the vertical axis. This point is equivalent to short-circuiting the solar cell, as the voltage on either electrode of the solar cell is equal. As such, we call this short-circuit current, or ISC. Let's look at this curve a little further and consider the power output of a solar cell. The power of a solar cell is equal to the product of the current and voltage. We will represent the product of the open circuit voltage and the short circuit current with a yellow box. This power is greater than the maximum power that a solar cell can produce, but it will be useful to calculate the solar cell's conversion efficiency. Now we can see the power as a function of the voltage. We can see that there is a point where the power generated by the solar cell is maximized. We call this our maximum power point. The voltage at this maximum power point is given here as VMP, which is the maximum power point voltage, and the current as IMP, which is the maximum power point current. You can see that the VMP is less than the VOC, the open circuit voltage, and the IMP is less than the short circuit current density, SC. This is always the case. The product of VMP and IMP gives the maximum power we can generate, which we denote here as Pmax, the maximum power. We define the ratio of the maximum power to the product of the open circuit voltage and the short circuit current as the fill factor, here assigned as FF, the fill factor. The fill factor essentially shows the quality of our solar cell. A greater fill factor implies that a greater fraction of the theoretical power can be produced. With these terms, we can define our conversion efficiency, eta. The efficiency of any such system is first defined by the power output divided by the power input, which we call Pi. With these equations, you can see that we can call the maximum power output simply Pmax. We could also define it as the product of the maximum power voltage and the maximum power current Finally, we can also use the VOC and the ISC and the fill factor. All of these terms are equal. You should now understand the IV characteristic of a solar cell. You know the basic external parameters, so VOC, ISC, and fill factor, and how to calculate the efficiency based on these values. Let's now look at how to model this IV behavior with electrical components in an equivalent circuit. So how can we represent a solar cell as an electrical circuit model? A solar cell is in fact a diode, and in the dark it acts electrically just like any other diode. However, illumination of the solar cell is what sets it apart. So let's take a look at how to model this electrically. Here you can see the so-called single diode model for a solar cell, as well as the equation that describes it. There's a lot going on here, so let's move through our schematic step by step. The first thing you may notice is the current source on the left side on the diagram. This represents the photocurrent generated through illumination, which we call here the I photon. Ideally, we want to pass the photocurrent to our load, represented in purple on the right. Here we see a diode with a current ID passing through it. This represents the solar cell diode characteristics in the dark. You will notice that this current is essentially a sink for the current. Some current will pass through this diode and this current does not reach the load. This actually represents the recombination that occurs in the solar cell, and you will learn a lot more about recombination later in this course. Next, we see two resistors. RP, the parallel or shunt resistance, and RS, which is the series resistance. These two resistors are there because the solar cell is not an ideal diode. We will look into the sources of these resistances in the next slide. Lastly, in our schematic, we see our load. We can see a current across it, I, and we see the voltage V. From this circuit, we can then solve the equation of determining the I as a function of V, the voltage. The equation additionally includes N, which is the diode ideality factor. In general, this factor is set to 1 in this equation, representing an ideal diode. Q is the elemental charge of an electron. The constant Kb is the Boltzmann constant and T is the temperature of the solar cell. Note that you're not expected to solve this equation. In fact, the equation cannot be solved algebraically, since the current across the load is a function of that same current. However, we intend for you to understand how different considerations in solar cell design affect these characteristics, and thereby solar cell performance. So let's take a look at how the JV characteristics of a solar cell can be affected by the resistances. First, let's examine the series resistance RS. RS is caused by the bulk resistance of the semiconductor materials and the metal electrodes. The contact resistance between the semiconductor and the metal also influences RS. You can see from this plot that as we increase our RS from 0 up to 10 ohms, the solar cell goes from a diode characteristic to an almost linear characteristic. We can easily see that increasing the series resistance decreases the maximum output power, even though the open circuit voltage and the short circuit current stay the same. Therefore, RS only affects the fill factor of our solar cell. Next, we look at the shunt resistance. If you remember, this resistance is parallel to our load, so we actually want it to be as large as possible. Otherwise, it acts as a sink for the current that will reduce power to the load. A reduced shunt resistance is caused by leakages across the PN junction around or around the edges of the solar cell, or defects, pinholes, and impurity precipitates in the semiconductor material. You can see here that if we have a shunt resistance of 0, our solar cell hardly produces any power at all. As we increase our shunt resistance by orders of magnitude, we can see the shape of our curve return to that of an ideal diode. The single diode model is good for electrically simulating a solar cell. However, sometimes it is insufficient, in which case an additional dark current diode is added in parallel. In this case, the first diode represents the dark diffusion current, while the second diode represents the dark recombination current. So now let's recap. We discussed the IV characteristics of a solar cell and looked at the single diode model. We then showed all aspects of the equivalent circuit and resultant equation. Finally, we considered the influence of series and shunt resistance on the IV characteristics of a solar cell. See you back in the next video lecture.